Creating models. Many events in real life are extremely complex, depending on many interrelated factors. However, often a much simplified model can match reality quite closely and allow predictions to be made. Slight adjustments to the model can improve the match. For example, the spread of a disease depends on many factors, such as the number of people in contact with the diseased person, the ease by which the disease is caught, the length of time the germ remains active on surfaces or in the air, how long a person remains contagious, and many others. A simple model can be produced, including some of the main factors, allowing slight changes in the nature of a disease to be inputted into the model to observe the possible effects. This can be very useful in planning in terms of the number of vaccines to produce, what stage schools will be closed, and so on. Radioactive decay, a random event, can be modelled quite closely using dice. A large number of dice are thrown, the sixes removed before they're thrown again, and so on. Each die represents an unstable nucleus, and a throw represents an interval of time. A 6 represents a decay. Each die has a probability of getting a 6 of 1/6, as 1/6 of the sides of the die are a 6, and the number of 6s gained depends on the number of dice remaining. The number of 6s from a particular throw will equal the probability of a 6 from one die, that is 1/6, multiplied by the number of dice thrown. Putting this in the terminology we use for radioactive decay, the number of decays per second will equal the probability of one particular nucleus decaying in 1 second, multiplied by the number of unstable nuclei still present. With radioactive decay, we call the number of decays per second the activity in becquerels, and the probability of a single nucleus decaying in a second is the decay constant lambda. The number of unstable nuclei is given the symbol n. So we can write that activity A is equal to decay constant lambda multiplied by number of unstable nuclei present, n. In a given time interval, the number of decays is equal to minus the change in the nuclei present, as for example, when we have 10 decays, we have 10 fewer nuclei remaining. So we can say that the change in the number of nuclei present over the change in time is the activity, and this is equal to minus the decay constant multiplied by the number of nuclei present. If the time interval delta t that we use is too long, the number of nuclei present, n, will have changed significantly during this time. To get the overall trend of the decays, we simplify the model by ignoring the fact that we have individual atoms decaying, and so we can reduce the time interval towards 0, and this we write as dn over dt is equal to minus lambda t. This is called the differential of n with respect to time. We can use a similar approach with a capacitor discharging through a resistor, as shown here. We know that the current through the resistor is equal to the potential difference V across it divided by the resistance in ohms. But also, the voltage will be that across the capacitor, which is given by the charge Q over the capacitance C. We can put these together to get that the current is equal to the charge Q divided by CR. But the current is also the rate of flow of charge, or the charge transferred delta Q, over the time interval delta t. So, we can write that the current delta Q by delta t is equal to minus Q over CR. The minus because, as the charge is transferred, we lose charge from the capacitor. Again, as the time interval tends towards 0, this becomes the differential of Q with respect to t, which we can write as dq over dt is equal to minus Q over CR. We can use a model to discover a lot about simple harmonic motion. Here we have a simple pendulum with the forces, its weight acting down, mg, and the tension in the supporting string T acting in this direction. These produce a force back towards the equilibrium position, F, and at the moment the pendulum has a displacement x from that equilibrium position. Velocity is the rate of change of displacement, so we can write that the velocity v is equal to the change in displacement delta x over a time interval delta t. But as the displacement changes, so does the force, so again we need to take the time interval close to 0 and write the differential, which would be v is dx by dt. Acceleration is the rate of change of velocity, which, as we tend towards a 0 time interval, becomes the differential a is equal to dv by dt, which we can write as the second differential of displacement, a is equal to d2x over dt squared. But for any body, acceleration is equal to the force divided by the mass, and for simple harmonic motion we make the simplifying assumption that the force is directly proportional to the displacement, or F is equal to minus a constant kx, the minus sign because the force F is in the opposite direction to the displacement x. This gives acceleration is equal to minus k over mx, where k is a constant, m the mass in kilograms, and x the displacement in meters. And so combining equations we get that the second derivative of displacement with respect to time, d2x by dt squared, is equal to minus k over m times the displacement x. This model is true for a mass moving horizontally on a friction-free surface between two friction-free springs with zero air resistance. It's very close to reality for a simple pendulum, as long as the maximum displacement angle is quite small. It's also close to reality for masses oscillating vertically on springs, and in many other situations. These models do not take into account every factor involved, and so will stray from reality in certain circumstances, but they can be very valuable in making predictions, and therefore overcoming potential problems before they occur.